Earlier in this course, I've said the more we learn about something, we often have to modify our understanding. So we've taught you the octet rule. You know that every atom needs to be surrounded by 8 electrons, except for hydrogen, which normally has 2. But there are also 3 types of molecules which will not have an octet. One of them is when they have an odd number. Another is when the central atom is electron deficient. And the third is when the central atom has more than 8 electrons. So again, we're modifying something that was originally found because they studied more. They found there were exceptions. I have an example for each. So here's nitrogen dioxide, NO2. How many electrons does nitrogen dioxide have? 5 from nitrogen, 2 times 6 from oxygen, giving us a grand total of 17 electrons. Well, there's our odd number, but let's work it through and show you what's happening. Nitrogen is in the center, oxygen is on the outside. I've used up 4 electrons, they have been used. I have 13 electrons left. I'll do it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So my oxygens have an octet, but my nitrogen does not. So let's say I start to move things around. Let's say that I take one of those pairs of electrons from that oxygen, place it in between, and here is what I have as a result. That still does not satisfy the octet rule. Oxygen is fine, but nitrogen ends up with 7 electrons. And that's where we would have oxygen double bonded to N to an O. This O has these 6 electrons. The other O has 2 electrons. The other thing that I could do is take the electrons from the other oxygen. Here I keep my same 6 on the outside. I have my nitrogen over here. I have my 2 pairs of electrons there, and I have rearranged it in this manner. So now I have O, N, double bond O, and I'm going to fill in the rest of my electrons. Again, that is correct. You must have all the electrons to have the correct structure. These 2 definitely are resonance structures, but they do not adapt or fit the octet rule. Trial and error. But the most important thing is, as soon as you see that odd number, let's say you have 4 molecules, you have to decide which of these is an exception. Well, one of the ways to tell is if one of them has an odd number. As soon as you come with that odd number, unless they tell you to draw it, you are done. So let's look at number 2. Number 2 says the central atom has less than an octet. Take a look at the periodic table where these 2 elements lie. You know, they're up in the left-hand corner. Let's do beryllium chloride, BeCl2. Beryllium has 2 valence electrons. I'm going to add to that 2 times 7. I will have a grand total of 16 electrons. I'll put the beryllium in the center. I'll put the chlorine atoms on the outside. So I've used 4. I have 12 electrons left. I'll put 6 on one chlorine, 6 on the other chlorine. And that is it. My actual acceptable Lewis structure looks like this, where I've drawn in the bonds. Now, why am I saying this is acceptable? It's because chlorine is more electronegative than beryllium. It tends to share only 1 pair of electrons with any less electronegative atom. You don't see chlorine sharing 2 pairs of electrons. And remember, chlorine is an S2P5. It's just 1 electron short of having an octet. So again, it tends to only form single bonds. This behavior is characteristic of the halogens. They simply do not form multiple bonds. I will also say that beryllium is very small. There really isn't room to put double bonds into it. And we'll talk about that again in chapter 9 as we talk about some different theories of covalent bonding. So the first exception was an odd number of electrons. The second one is where the central atom has less than an octet. And the two examples we have for you, beryllium chloride and boron trifluoride. Finally, this one students have a lot of questions about. This is where the central atom has more than an octet. Well, which row can we have d electrons? I'm going to work backwards. If n is equal to 3, we can have s, p, and d. If n is equal to 2, we can have s, p. And if n is equal to 1, we can only have s. So you know this part from chapter 6. Now let's show an example drawing Lewis structures. I have some molecules listed there, okay? Sulfur hexafluoride. Oh my gosh, that is going to have a massive number of electrons. 6 from sulfur, 6 times 7 will equal 48 electrons. Well, first of all, how am I going to draw it? We normally only put like 8 electrons around an atom, but sulfur is an exception because this molecule does exist. It uses 6 times 2, which is equal to 12 electrons, just to go around the central atom, and it has 36 electrons left. Now I'll point something out. If I have a terminal atom, in order to complete its octet, it needs 6 electrons. If I do 36 divided by 6, I get the number 6. So I'm going to be using up each and every one of those leftover electrons, putting them around the fluorine atom. Takes a while to draw, but there they all are. That is the structure of sulfur hexafluoride. All of the electrons are left. 36 minus 36 equals 0. This only happens with elements in the third period because they have these d orbitals that can be used for bonding. Now, I'm going to do one more example here because let's just say in chapter 9, you're going to tell me that this is an octahedral molecule. You're going to tell me it has 6 bonding, 0 non-bonding electrons, and you're going to also tell me that it's nonpolar. So it's really important that you're able to draw these structures in chapter 8 so that you can move on to what we need to talk about in chapter 9. So let's do one more. Let's do the chlorine tetrafluoride ion. Very, very odd, isn't it? Chlorine has 7. 4 times 7 is my 4 fluorines. Subtract 1 because it is a cation, 34 electrons. So let's see what happens with this molecule, ion. I will put chlorine there, and I'm going to draw the bonds in right away because that just makes my life easier and your life easier to look. 34 minus 8 is 26 electrons. So remember I said something about 6 electrons around each terminal? Well, 6 into 26 goes 4 times, and there are 2 electrons left. That's the math. But let me draw in all those electrons. My first 6, my second 6 to give an octet, my third 6 to give an octet, my fourth 6 to give an octet. Put the brackets around, put the positive sign there. I have used up, I had 26 electrons, I used up 24, I have 2 electrons left. Where am I going to put them? I'm going to put them around that central atom. And you might find that to be very, very, very strange. But that is the material that we will have. And when we're in chapter 9, you will be giving me a molecular structure where chlorine is in the center, the 2 fluorines are on the z-axis, and the other 2 fluorines are in the xy plane, with a lone pair of electrons. Again, this is what has to happen in chapter 9. So in order for that to happen, you've got to be able to draw these structures in chapter 6. Please do not memorize. It is not the way to go here. What you want to do is the silly thing I do. Do the math. 7, 4 times 7, minus 1 is 34. Plop those things down around that central metal atom. Figure it out. Because what you'll have here in chapter 9, you'll say 5 electron domains. We have 4 bonding, 1 non-bonding. On your midterm number 3, it's chapters 7, 8, and 9. You're going to be pressed for time. I know that you will be, because everybody is every semester. It's kind of towards the end of the semester. So while you're in chapter 8, knock this stuff off. I kind of don't even call it chemistry, because it feels like I'm drawing somewhere. All right? So practice, practice, practice. We only have one section left in this chapter.